Mic check, mic check, mic check. Hello, hello, hello. 1, 2, 3, 1, 2, 3. Mic check, mic check, mic check. All right, we are good to go. Hello. We are back at it again with another episode of Conquering Physics, where we are just going through these problems. At least one problem a day. Maybe we'll take Sundays off, I don't know. But today's problem deals with momentum. That's the section. And the problem for today is, what is the moment of inertia about an axis through its center of a sphere of radius r, mass m, and density varying with a radius as rho as a function of r is equal to ar. So let's just try to draw this out. So we know that we have a sphere, right? And it has mass m, radius r, capital R, and the density is a function of r is equal to ar. Okay, and we want to know what is the moment of inertia. And so I kind of took a little peek, but I would have remembered it anyways. So I know that the actual mass of a system is equal to the integral of density, right, of the whole entire space. If you want to calculate a moment of inertia, you basically have to incorporate an x within this. And so if we were to do this for a sphere, if you remember the Jacobian or the transformation, if we were to work in spherical coordinates, it's a triple integral. And so we're going to put the radian components all the way in the back because we'll deal with that last. Okay. And so this is going to be the, I believe that these two together are considered the azimuthal component. And so we have x in this case is actually r times rho to the r, because in this case it's only going to be dependent on r. And then you need the Jacobian part, which ends up being 2r sine theta d theta d phi dr. Okay, and so we could actually move all of these pieces out respectively. So this is basically some multivariate calculus going on right here. We can move the r components out of these because they're not dependent. It's going to be r to the third power, and then we can do these two together. d phi. Okay, so you work out this integral, you'll get a 2. I guess I should probably work it out just in case anybody doesn't know how to work it out, and you know that I'm not just making numbers up. And so the integral of sine is negative cosine theta, and we evaluate it from 0 to pi. And you may ask, well, what is negative cosine theta? Well, cosine theta is -1, so -1 times 1 is 1. So we get 1, and then minus cosine of 0 is equal to 1. So we get, and this minus contributing here is -1, so we get 1 minus minus 1, which is 2. That's how I knew that was a 2. Okay, and we can move this 2 out. And now we solve for this. And I hope I don't really have to explain this. This is just 2 pi. If you wanted to actually evaluate this out, you can say this is equal to phi evaluated from 0 to 2 pi. and you get 2 pi minus 0, which is just 2 pi. So this is 2 pi. Okay. And so the azimuthal component, or the spherical part, if you don't have any dependencies on phi or theta, usually you get a 4 pi out. The 2 from the theta component, 2 pi from the phi component. And so we'll just pull all this out. 4 times 4 pi times the integral from 0 to r to the third. And remember, what was this? AR. So we'll actually plug this in right here. To the r power. And so as we're working this out, we can pull the a out because it's a constant. We get r to the fourth dr is equal to 4 pi a, and then the integral of r to the 4 is r to the 5 divided by 5. And we evaluate from 0 to r. This is now equal to 4 pi a big R to the 5th power divided by 5. And let's see. Oh, so this is interesting. So we actually don't. So this is what our moment is, right? But this problem, the way it's worded, is what is your moment as a function of m? We want to know m, and we were told this is m. And so right off the bat, we know we actually have to calculate this out. And so we just calculated this, I, but now we want to know in terms of m. And so we have to calculate m. M is equal to 0 to r. So it's going to be the similar calculation, but we actually don't have this. So I'm just going to cheat a little bit. And now we have r squared, rho, this, and then we have our 2 pi right out here, or 4 pi, because it's the same factor. This integral is going to be the same. Nothing changes because the only difference was we had an r out here. So we're still going to have our 4 pi. So we have 4 pi, and now when we're evaluating this out, we have a r to the third dr instead of to the fourth. And so this is equal to 4 pi, we evaluate this out, a big R to the 4 over 4. And this is going to be equal to pi, a pi r to the 4th power is equal to m. And so, as we can see here, if we were to factor out an a pi over 4, we get 4 over 5 r a pi r to the 4. And this is going to be equal to 4 over 5 rm. And unfortunately for us, these are none of the answers. It says that we are actually missing, or we should actually have an r squared. So, because our options are a 4/3 m r to the 6, b 4/9 m r squared, c 2 to the 5th m r squared, d 2 pi over to the 3rd power r squared, e 4 pi to the 5 mr squared. Okay, one thing I actually just realized is I actually calculated for the center of mass with this. This is not the equation. What the equation we actually need is squared right here. But let me double check. Yep, that's it. It's this component should be squared. So if we were to change the math real quick, squared to the fourth, this is all the same, to the fourth, to the fourth. And so now this should actually be to the fifth. And rather than 5, we would get to the 6, 6, 6. And this would be r to the 6, r to the 6, 6, right here. And we would have a squared here. And we have a squared. And this is 2 to the third mr squared. And do we have an answer like that? This is actually squared. Yes, we do. It's D. Awesome. And so the reason why I don't want to throw away any of my errors and you can watch me correct them is so you can try to see how one can go about going back to where you found your error, try to correct it very quickly, and try to just continue on. That way you save as much time as possible. You don't want to find out, oh, I have an error, and you realize it, and you feel like you're doomed. The correction only took a little bit. Notice how just taking the time to check if we were correct to see if it makes sense. Also, if we wanted to check units, the units of inertia tend to be a mass times some type of distance squared. And so we would have been able to see right away that ours was off. It's just been a while since I've dealt with that. But that's the problem for today. If there's any other questions, feel free to leave a comment, and I'll hope to be able to solve any problems others might have in the future. Until then, take care, keep on, keep it on, keep learning. Bye bye.